Hey everyone, this is Mr. Geiselman here with our chemistry unit radioactive decay video. So today what we're going to be looking at is explaining why atoms go through radioactive decay, determine what type of decay it is by the products and the reactants, and then we're going to be able to describe the properties of alpha particles, beta particles, and gamma rays. Today what you need to do is you need to watch this Edpuzzle, take notes on it. If you're in my class, watch the Edpuzzle before attending the Google meeting, all right? And then make sure that you have everything else done that's assigned with this post. So what is radioactivity? Radioactivity, by definition, is when an unstable nucleus emits one or more particles of energy in the form of radiation. So when radioactivity will occur is when a nucleus is unstable, meaning it's a little bit too big, there's too much energy inside of it, the number of protons to neutrons is off, and it's going to emit radiation. And that can be just energy, or it can actually be a physical particle being shot out of the nucleus of that atom with some of that energy. We also call this nuclear decay. Decay means to break down, and this is occurring in the nucleus of the atom. So that's why it's called nuclear decay. So if we were going to be able to use that in a sentence, unstable atoms are radioactive. You probably know some radioactive atoms, and there's a lot of different ways that different types of radioactivity are actually useful to us, and we're able to use them in pretty significant ways. So nuclear radiation really talks about the particles that are released from the nucleus during radioactive decay. And they can be three different things. They can be protons and neutrons, they can be electrons, and they can also be a photon. And a photon is an energy particle. It's not really a particle, but it's a little package of energy, and we'll talk a little bit more about those. So there's three types of radiation. You can tell from here, there's alpha radiation, which releases alpha particles, beta decay, which releases beta particles, and then there's finally gamma decay, which releases gamma rays. I think you'll notice that alpha and beta are particles and gamma is rays. Gamma is going to be a packet of energy. That's going to be that photon. There's not going to be any mass associated with that, where the alpha and beta particles are going to be physical pieces of that atom are decaying. All right, so looking at the picture there, which one, alpha, beta, or gamma, do you think has the most energy? Hopefully you picked gamma, because you can see that gamma radiation will actually go through your hand, so it will penetrate your skin. It can actually even go through aluminum. And then something that would have to stop it is lead, like just about, I believe it's 7 centimeters of lead will stop gamma radiation, which is a pretty significant amount of lead. Lead is really good at blocking radiation because it's a very dense material. Alpha radiation, we'll talk about it a little bit. Alpha particles are usually stopped by things like your clothes or a piece of paper. Beta is a little bit more high energy, and it takes a little bit more to stop that. So the alpha particle is a large positively charged atom that is released in the decay of radioactive elements. So when an alpha particle is released, what we're really releasing is a helium atom without electrons. Helium has 2 protons and a mass number of 4, meaning it also has 2 neutrons. So the 2 protons are here in red, the 2 neutrons are here in yellow. So that positive 2 charge means it's going to be positive because there are no electrons to balance that out. It has a mass of approximately 4 AMUs, right? And this one is going to be stopped by a sheet of paper. This isn't a ton of energy, but if you think back to first trimester, force equals mass times acceleration. Well, this one's going to have our biggest mass when we look at the masses of all of them, right, at 4 AMUs. So it's going to take a lot more force to accelerate it. It's not going to be moving as fast, and that's why it's not going to have quite as much energy all right, as the other types. It's actually really useful. Americurium 121 is an example of a radioactive um, element. It's an atom that will release alpha particles, and you actually have them in your house. They're used in smoke detectors really often. So they use that and they emit alpha particles, and that's part of the reason that they're able to detect things that are really small, like smoke particles in the air. So if you remember an alpha particle, it's basically a helium atom without electrons being emitted from the nucleus. How does this actually occur? It occurs when a nucleus is unstable and it has too many protons. So there are certain elements that don't like to remain for a long time. They'll form and then they'll break apart quickly. And this is where alpha decay would occur. It emits that alpha particle and some energy with it. So that alpha particle reduces the number of protons and neutrons, right? It reduces the number of protons by 2, and it reduces the number of neutrons by 2, so the mass number goes down by 4, and it emits some energy. That alpha particle, 2 protons and 2 neutrons, it's the same as a helium nucleus, and I think we've said that enough. All right, and the decay makes the atom more stable. It's happier there, it's at a lower energy, it likes to be there. So the nucleus is here, and it's going to shoot off that helium nucleus, right, with 2 protons, no electrons, and 2 neutrons. So if we go through alpha decay, when we release an alpha particle, we're going to subtract that helium nucleus from the original atom. So that means we're going to reduce the mass number by 4 of the atom, and we're going to reduce the atomic number by 2. So we'll go through an example of that. So it's really important to remember that the masses of the atomic number, the mass and the atomic numbers on both sides of an arrow, that's going to be our chemical equation, all right, need to be equal. So they need to be balanced. So down here at the bottom, we have radium 226, so 226 mass number, 88 for a atomic number, is going to go through alpha decay. We know it's alpha decay because we have the helium atom being ejected. That's one of the signs that it's alpha decay. So if we look at this, we're going to reduce, you can think of this as an equal sign, we're going to reduce the 226 by 4. That's going to give us 222. 4 plus 222 gives us 226. So that has to be equal on either side of that arrow. Down below, 88, right, is equal to 2 plus 86. 86 is our new atomic number, and that's going to give us the element radon. So it will go through that type of decay and form radon. We check if it's balanced. 226 minus 4 equals 222. Looks good. 88 minus 2 equals 86. It's good. So it's exactly what we're looking for. Beta particles then are the next type. So beta decay occurs when a small, fast-moving, negatively charged particle is emitted during the decay of radioactive elements. So an unstable nucleus will release essentially an electron from the nucleus, and we'll talk about how that actually happens in a second. But electrons, remember, don't have any mass, right? It's so small we don't even count it. So it has a mass number of 0, and it has a proton of -1, right? But that's because it's negative. Electrons are negative, and we'll talk about how this works out in a sec. So the charge on that atom is, the charge on the beta particle is -1. Its mass is so small that we don't even count it. But because its mass is so small, it gets to be moving really, really quickly. And that's why it's faster. And that's why it has a little bit more energy, and it can cause a little bit more damage to materials. So it's stopped by 3 millimeters of aluminum, or about 10 millimeters, 1 centimeter of wood. So it takes a little more to stop a beta particle from damaging something. If a beta particle hits your skin, your body's going to absorb that, and that can actually damage the cells in your body. It can cause mutations in your DNA, and eventually mutations can cause things like cancer. So that's why radiation and nuclear radiation is specifically bad for you. Strontium-90 is an example of a beta particle that we use a lot. It's actually used to treat cancer in radiation therapy. So doctors will focus that beta particle decay towards specific parts of a person's body, targeting tumors during cancer treatment. The reason why radiation therapy and cancer therapy in general is really tough on the body is because we're trying to kill those cancer cells. And it's really tough on the healthy cells in the body too, because this will kill them as well. That's why cancer patients usually lose weight and have other very, serious side effects when they're going through treatment, because they're not only killing cancer cells, they're killing healthy cells as well. When we look at beta decay, it comes from an unstable nucleus, and it's going to emit that beta particle and some energy along with it. A beta particle is a little bit of a goofy thing, though, because it starts as a neutron that breaks down into a positive and a negative piece. It breaks down into that electron that is emitted from the nucleus, and it breaks down into a proton that stays in the nucleus. This changes the atom entirely. So the proton stays in the nucleus, increasing the atomic number of the atom, and the electron gets emitted. In turn, this makes the atom more stable. So what happens is a neutron undergoes a change. The positive piece of the neutron and most of the mass stays in the nucleus as a proton. And then the electron is shot out into the area outside of the nucleus. When we look at beta decay, we're releasing a beta particle. And this kind of goes back to that 0 and -1 that we looked at earlier. The mass number does not change because a beta particle has almost 0 mass. So we don't even have to account for how much mass was lost. But the atomic number is increased by 1 because that neutron that gave birth to the beta particle and the proton stays in the nucleus. So the atomic number now with that extra proton goes up by 1. So the masses of the the masses and the atomic numbers on both sides of the arrow must be equal. So when we look at this example equation, calcium-47 can go through beta decay. We can think about the arrow like an equal sign. 47 equals 0 plus 47. That looks like it's balanced. Now, if we looked at the bottom, 20 for an atomic number equals -1 plus 21. -1 plus 21 equals 20. So it looks like it's balanced here. Is it 47 minus 0? Still equal to 47. Equal on both sides. 20, right, minus a -1 or plus 1 equals 21. And that's how we get the products in a beta decay reaction. The next type is gamma decay. Gamma decay is probably my favorite because it's a little more consubstantial, because it can cause some serious issues for living tissues, but it's also the easiest mathematically. So gamma rays are represented by this Greek letter gamma. It looks kind of like a funky Y or a funky V. Well, it's the Greek letter gamma, and it's a high energy photon emitted from a nucleus during fission and radioactive decay that can cause damage in matter. So the atom is either going through a split where it's breaking into two completely different pieces, or it's just got too much energy inside of the nucleus. So it's just going to release this ray of energy as a photon. It has no charge and it has no mass. So it's not going to affect the number of protons, the number of neutrons, or the mass number for the atom. This is going to be stopped by 60 centimeters of aluminum foil, which is a lot. That's over half of a meter worth of aluminum foil, or 7 centimeters of lead, which is still a pretty substantial amount. So that external beam radiation therapy, so this is like really aggressive radiation therapy for cancer patients, will use gamma radiation. Gamma radiation can also be used to sterilize medical equipment and a few other things, but it's really dangerous to living things because it has so much energy. It can wreck and mutate the person's DNA in their cells, and that can either cause the cells to die or it can cause the cells to not function properly, and that can lead to things like cancer. So gamma decay is when the nucleus is in an excited state. It's got a lot of energy and it needs to get rid of it. So to get rid of that energy, it's just got to release it at some point, and that will make it more stable. It emits that packet of energy or that photon, the gamma ray, it's not a particle, it's a gamma ray. And it often actually happens after an alpha or a beta decay has already occurred. It just releases that extra energy that's stored in the nucleus, and it does not change the number of protons or neutrons. So here would be an atom. It's excited. It gives off that photon of energy, the gamma ray or the gamma particle. It's really a gamma ray. And then nothing changes to the atom other than it loses a little bit of energy. The gamma ray is released. The mass number does not change. The atomic number does not change. So when we look at these equations, I think they'll be your favorite too, because if you start with an element on this side and it goes through gamma decay, it's going to be the exact same on the other side because gamma rays have no mass and they have no proton, so it's not going to change the atomic number. So what you start with is what you have at the end as well. So what type of nuclear radiation is present below? Hopefully you're able to figure out that because the helium atom is there, it has to be alpha decay. Let's try one more. What type of radiation is below? Again, the particle being released, or the components, right? We have our products and we have our reactant, we have our reactant, we have our products over here. That's going to tell us exactly what's going on. And in this case, we have a beta particle being released, which tells us it's beta decay. Last one. Let's take a look at this one below. What type is it? Hopefully you figured out, because the Greek letter gamma is right here, that it is going to be gamma decay. So hopefully those were pretty easy for you. They were all the examples that we looked at earlier. So hopefully they should have just been a simple recall back to what we did before. So after this lesson, you should be able to explain why an atom undergoes nuclear decay, because it has just a little too much energy or it's unstable. You now can determine what decay is taking place by the products and reactants, whether it's a gamma ray, an alpha particle, or a beta particle being released. And then you can describe the properties of an alpha particle, beta particle, and a gamma ray, knowing that alpha particles are positive with a +2 charge. They're just like a helium atom without any electrons, and they don't do a lot of damage to living things. They're usually stopped by a piece of paper or something even pretty insignificant. Beta particles are essentially an electron being emitted from the breakdown of a neutron. We know that beta particles can damage cells because they have enough energy to break the bonds in our DNA, causing mutations. And now you know the gamma ray is a packet of energy being emitted from an excited nucleus, and they have tons of energy and they can really do a lot of damage to the cells in our body. All right, we're looking forward to seeing you guys at the Google meeting. We'll talk to you guys then.